Now the next exercise, exercise 2b, will concern the splitting of this feature space of regression trees. A regression tree splits the feature space into separate regions. The algorithm must therefore determine the value of the respective variables at which the data needs to be split first. Draw a 2D coordinate system of the feature space with the above points, these points here, only features, not the target in it. Then determine by iteration the first optimal split as 1 for the variable x1. Use the optimality criterion from the lecture. So let's do this. So I already draw this coordinate system and the points inside it. Now next I will note above every point the y value. So this is here, y is equal to 10, here y is equal to 7, here y is equal to 8, here it's equal to 3, here y is equal to 4. Okay, now what should we do? We should find the splitting value as 1 by separating space into regions. And this is part of the recursive binary splitting. Okay, so the resulting regions will be R1, and R1 are all the points of the feature space where the criterion that the respective point is smaller than our split value is met. Okay, so we have a certain split value, and everything that is smaller than this value, so every point belongs then to this set. Same goes for the second region, which is dependent on the variable we are looking at. So this is the variable index. So it could be a splitting at the region at the y-axis, x1 axis, or at the x2 axis. And second, it's obviously dependent on the splitting value. And the resulting region R2 of this binary splitting will be the leftover region where x is greater than the splitting value. All the values inside the feature space that fulfill this condition are inside this set. Okay, and how should we split this? We should split this such that our criterion is fulfilled, and this one you know from the lecture. Okay, so this criterion should be minimized, or this loss here should be minimized, and I will explain it in a second. Okay, so it should be minimized with respect to S and the and y hat r1 and y hat r2, which are our estimated values inside the regions. And so this loss function here on the first part is the sum of the difference between our y values and our estimated values for a point that lies inside the region 1, and on the right side here it's the same for region 2, so the difference between the y value of a point lying in region 2 and our estimator estimated value for that point lying in region 2. This squared difference here, and the sum of this is this right part. Okay, so it's basically somewhat similar to the sum of squared residuals, if you think about it, where we also have the difference between the true value and the estimated value. And here we split this up into the two regions. And if you think about it, if the regions are split at the best possible level or value, then this should be in sum smallest possible. And what we will do now is we will split our feature space. Hold on. After every point, and after every split, we have a look. We calculate this loss function, or the loss we calculate with the loss function, and pretend just that we use the split, calculate the loss function, save the loss. Then we take the next split, pretend as if we use this split now, then calculate left-hand side loss, right-hand side loss, sum it up, save that loss, and do this for the third split and the fourth split. And we don't need a fifth split because then it would be only one region. That wouldn't make any sense. So yeah, that's what we do. We split now recursively, binary, so we have two regions resulting from the splitting, then calculate the loss, and then at the end, when we have calculated the loss for every split, we will compare the losses, and the split that produced the lowest loss will be the one which we consider optimal. Okay, so let's write down first, how do we get our y hat here? Well, from the lecture, we know that for a fixed s, the following is true. So the first part here is our estimated value of y for all points in the region R1, and this we define as the average of all the y values of the points inside that region. Same goes for the second one. Our estimated value for all the points inside region 2 is the average of the y values of all the points inside region 2. So, and what is S? Let's determine S. From the lecture, you know that Sj is so Sj is defined as such. So what does that mean? I have for r equal 1 to n minus 1. So now let's say j is equal to 1, which is the case for our exercise because we only want to have the split on the x1 for the x1 feature. Now, so it would be s1. Then this would be, then s would be 1 half of times 1/2 times the sum of the x value of this index r plus the x value of this index r plus 1, and r is the point left from our split, and r plus 1 is the point right from our split. So our first split here is basically there r equals 1, and then we must calculate 1/2 of x1 and 1 plus x1 2. Okay, this would be the s1 for our first split here. So let's write it down. Here we split x1 We search for x1 by repeatedly iterating, no, not by repeatedly iterating, by iterating over r equal to 1 until n minus 1, and repeatedly splitting the feature space into R1 and R2, then calculating our loss and comparing these losses at the end to find the optimal S1. Okay, so that's basically what I already said. So we split in this binary fashion the feature space in two parts. At every split, we calculate our loss using this loss function here. Then we save that. Then we take the next split, calculate the loss, the next split, calculate the loss until we are done. And then at the end, we look at which split we have the smallest loss, and then we look, okay, what S did we have at this split, and then we use that as our optimal S. Okay.